Be interesting. So heaps, this is recording the screen, right? Yeah. So the heap is a place. It's a magical place where you can make things dynamically in memory, right? You make your tree nodes on the heap. We make our list nodes on the heap. This is completely different to that, unfortunately. We have reused the same exact name. We pluralized it, I guess, but you can make a singular heap data structure, and it will look a bit different, unfortunately. All right, it has nothing to do with dynamic memory, but that's okay. All right, so not to be confused with the heap. We did have stacks. We also had something similar with a stack, right? We had the stack data structure and then also the runtime stack that stored like function calls and where they were to return to, like the stack of work to be done. And those are actually quite similar if you think about it. It's like storing data versus storing function calls in the same kind of style. Unfortunately, heaps and the heap have nothing at all to do with each other. A heap data structure is just a place to store stuff, just like trees and lists. So just keep that in mind throughout this lecture. It's interesting. All right. So let's start with heaps, the data structure now. Very, very exciting. So yeah, let me try and motivate to you why we might want another data structure. We've studied lists. We've got arrays under our belt from CSCI 40. We've got vectors now. We know how the sausage gets made there. We've got trees, binary search trees. What else could we possibly want? Hash tables, right? So here's an idea that will motivate a heap. All right. So what a heap is, it's a data structure that's really, really good at finding the maximum thing in constant time that you've put into it. The maximum thing. For a given definition of maximum, you could also define maximum to be the maximum smallest thing, and now it'll give you the minimum. All right, so you can get the max or the min out as easy as you would like, very quickly in constant time. So yeah, it could be max or min. It's like define maximum to mean the maximal smallest thing. A good example of that is like a priority list. If you're, say you work at a hospital, or like you've got, you're triaging patients or something like that, right? You make the app that does that. And so there are going to be different patients who come into the doctor's office. Let's say, I don't know, here's the doctor's office. Here is the door, and here's a new patient coming in for the day, and you've already got a bunch of other patients, right, that are just sitting around in the waiting room waiting to go. Maybe this is the emergency room or something. All right, are you going to order these patients in an array? What else could we do? We could order these patients in a linked list. We could put them in a tree. But kind of the idea is somebody new comes in, you're going to add them to this list, to this array, to this tree, right? And you're going to the doctor's always going to want to deal with the person that's the most critical at the current point in time, right? So you're going to really want to find the maximum thing very quickly, where you can like give a number to how severe the patient's ailment is, something like that, right? So if you want to have all these patients, you put them in some data structure that we know right now. What are we going to do? How can we find the maximum? We could sort an array or a vector. That would work. That would be n log n time. Now it's at either the front or the end, depending on how you sort it. But you always have to sort when somebody new comes in. That would work. You could also just go through it in linear time to find the maximum, couldn't you? Right? That would be a thing. Same with a list. With a list, you can't really sort it very easily. You just go through it, linear time, keep track of the maximum. So it would take a while. It would be O of n, right, for a vector or a list to find the maximum thing, wouldn't it? And that would be very, very important to do very quickly if you were in like a life or death situation. Same with trees. If it was a balanced tree, you can do it a little bit faster. Just keep going right forever. You know that, right, from our discussion on successor and predecessor. The biggest thing in the binary search tree is just you go to the right forever. And if this is a balanced binary search tree, then it would be logarithmic time, because the height of the tree is relative, or it's proportional to the logarithm of the number of nodes. So that's a little bit better. But it's not constant, is it? So there is improvement. There's room for improvement here. And that's what a heap gives you. All right. So what a heap is, it's a little weird. I'll show it to you in a different way in a second. It's going to be very odd what we're about to do. But a heap, I want you to think of it conceptually as just a special kind of binary tree. All right. So this is an example of a heap that is called a max heap. It holds the maximum. It lets you get the maximum very quickly and easily. Okay. Do you see why it's constant time to find the maximum in this heap? If the nodes are the things that are in them. It's just right at the root, yes? So the root, which you can go to by dereferencing a pointer very quickly, if you want to think of it as a tree like this, the root is the max. You could just as easily have made a min heap, where you always keep track of like the minimum thing on top. Like 33 could go over, bigger things go on the bottom. There's no concept of, it's not a binary search tree in that like 13 can be over here on this side. It's okay, this is a min heap, where it holds the minimum thing on the top. And there's going to be a sense of order still, though it's not like binary search trees. This is a correct min heap. It's not a binary search tree. I think that's clear to us, right? So how it works is it's a complete binary tree. This is the reason why we learned this word complete. All right, it's a complete binary tree. So every row it's filled in, it's perfect up until the last row, and all the elements are filled in from left to right. Remember that? This is going to be very, very important for heaps. All right. So the next element would have been the left child of 3, then the right child of 3, then the left child of 25, then the right child of 25. That would be the order in which you would put more nodes in this tree. You'd have to shuffle things along because you want to keep the maximum at the top, but that's how it's going to work, right? So remember that a complete binary tree is where all the levels are filled in except for the last one, potentially. And then the last level is filled in from left to right, all those elements, all right? So if we are enforcing this, that means that every heap is a balanced tree and we get that logarithmic height for free, okay? If we can keep this in check, okay? So that's how that works. And hopefully you can kind of tell that like we're going to put bigger things on top. That's how you force the maximum up there, all right? So that's going to be, there's going to be an algorithm, and it's called the heap property, all right? We're going to enforce the heap property. So for a max heap that's going to store the maximum up top, that means that every parent, the key in it, remember that we're using key to mean like the value that's stored inside of a node, if this is a tree, it's going to be greater than or equal to the keys of its children. Duplicates are fine for a heap. Just like you want the maximum, it's okay if there's others, just like make sure that the biggest one, even if there's duplicates, is at the top somewhere, okay? So that means every parent's key is going to be greater than or equal to the keys of its children. That's what we're going to enforce, okay? So this is true for everybody. 100 is bigger than those guys, 19 is bigger than these guys, and that's what it means to be a heap, all right? Can you kind of intuitively see that if you enforce this fact at every node, it forces the max to be at the top? If you do that, it's going to force the maximum to be at the top, even though it's not a binary search tree. If you just keep this in check, like just naturally, it's gonna float up there. Okay. So same for a min heap. If you wanted to do a min heap, it's just like every parent is less than or equal to the keys of its children. That would again force the minimum up to the top if you kept that in check. Okay. So keep in mind that this has nothing to do with binary search tree stuff anymore. It looks maybe similar, but it's not. Notice how like one can be over here and it's still a max heap. You see that? Everything is fine in terms of the max heap property. Okay, so that's how that works, and so that forces the max or the min to be at the root because of this. If you were to change elements, like you should be allowed to mess with stuff eventually. Like let's say that I made this like 101 or something. This is now no longer a max heap. I would have to do something about this. I would have to move it up. All right, so if I change this to like 101, this is no longer a heap. That's one thing. We'd have to move it up. You'd have to keep that in check every time you change things or add stuff. And then if you were to add something, it would go right here. Like let's say you add a 0 here. It would be okay for it to be right there, wouldn't it? Like a 0 could go right there. It would be the left child of the 3. Okay, does that make sense to us? This property, it's going to be a complete tree. Last row filled in from left to right. Everybody else is perfect above. And it's got one of these properties. If it's a max heap, all the parents are bigger than or equal to their children. If it's a min heap, all the parents are smaller than or equal to their children. And as long as you keep that going all day long, it's going to force the thing we care about to be at the top. To be at the top. All right? That's what's going to happen. Any questions about that before I show you how it's going to be done? Kind of hopefully intuitive, all right? So enter the heap data structure. So I've drawn this as a tree. It's going to be interesting. This is a very fancy kind of tree where we want it to be complete and filled in this exact way. I guess you could use nodes and pointers to make this happen, but it would be a little clunky. And so it's like, this must be really hard to do if we're going to use nodes and pointers. The secret is, it's like we're being trolled from the early ages of the internet. We're going to represent this tree with a vector. Just take a minute for that to sink in. That sounds disgusting, right? We are going to represent a tree with levels and nodes with something that is a straight line. Yeah? We're going to use this to mean this. Somehow. Those pictures are going to equate. And it sounds very weird, all right? Let me show you why this is actually a great idea, all right? So if you think about it, you could also use an array, but you probably want to be able to resize it. So like you'd have to make a vector if you had things, if you had multiple things. So the vector is probably the best answer, but you could use an array if you had extra space. But here's how we're going to turn this into a vector. We're going to make this index 0, and it'll go in level order like you were doing a breadth first traversal. This will be index 3, 4, 5, 6, 7, 8, and 9, 7 and 8 for now. And so this is how the vector will be arranged. We're going to have 9 elements. Did I count that right? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll have 100 here, then 19, then 36, then 17, and then 3, and then 20. We're going to store it in this exact way, 25, and then 1, and then 2, and then 7. So that's quite nice. And do you see how easy it is? Well, let's make this a vector v, index 0, 1, 2, 3, 4, 5, 6, 7, 8. Do you see how easy it is, first of all, to get to the root? So like go to index 0, that's where it is, right? Sure. Do you see, bless you, do you see how very easy it would be and how easy it is to keep this a complete tree if we're going to play this game? Because the next element is going to go at index 9 and it's going to represent that idea right there, right? We're just going to use that. We're going to use that idea to represent that. So that's not hard at all. It's easy to keep it a complete tree given what we're doing. It's like, all right, that was going to be forced to be index 9. Like if I push back, it's going to go to that place. And then we can move around this tree without pointers, but with indices. Let me show you that there's a way, all right? So if you are at a certain node, you have an index now, or don't you? Because this is now a vector. So let's say you're at index 1, and you want to go left. This is going to work for any node. You take your index, you multiply it by 2, and you add 1. That will always work. This is very cool. So in constant time, you can get to the next node by calculating an index and going to that index. So it's as if you dereferenced a pointer in a sense. So going left, 1 times 2 plus 1, that is 3, yes? Going right, just add 1 more. 1 times 2 plus 2, that makes 4. To get to your parent, you do have to do a little bit of subtraction first, but it's like a division by 2. Just go up, I minus 1 over 2. So like if you're at index 1, 1 minus 1 is 0, over 2 is 0 still. That works for that one, and it works for everybody else in the tree. All of those are always going to work. You got an index 4, you want to go left, times 2 plus 1, index 9. Is that not beautiful? You want to go to the parent of 4, it's still 1. You're going to do integer division. It's going to be 4 minus 1 is 3, divided by 2, integer division land, that is 1. You can get anywhere in this tree with indices by representing it with a vector. And it keeps it complete, because like you add the next thing, is going right there, and it's going to be representing this next node in the correct place of a complete tree. That's beautiful. Do we see how lovely that is? Are there any questions about this? So we're using a vector to represent a complete tree. And it's very easy to move around it just with some math instead of pointer traversals. Pointer dereferencing. Okay? That's a weird idea. Are there any questions about that idea? It is cool. It is really cool. I hope you agree that it's very cool. So let's talk about, we got space complexity. We got to deal with like keeping it a heap as well. But like space complexity is easy. Just like, okay, you want to put a bunch of things in the heap. you're going to have that many things in your vector, aren't you? No more, no less. You're going to push back that many things. You're going to have to shuffle them around to keep it as a heap, of course. We'll get to that. But if all you're doing is you're storing the data at the particular indices of the vector that you care about. And so if you got n nodes, n keys in your heap, then you have a size n vector. The space complexity is linear, which is as good as you could hope for, right? So it's O of n space complexity. You're storing as many indices in your vector as there are things in your heap. Does that make enough sense? Questions about that? So it's linear space for storing all your n things. You're not taking up any extra space. You don't need any extra size elements in your vector. Like, for example, we needed for hash tables to keep collisions down. We needed some extra room. Still was linear space, but you get the idea, right? So that's that. It's not too horrible for the space complexity. And we can see if we keep it like this, like getting the maximum is constant time, just go to index 0 always, or the minimum if it was a min heap. That would work. And now let's get to the algorithm. Are we ready for the algorithm? Like if I add something, maybe I push or insert 101 to this heap. What do I do to make it to keep it a heap? I gotta like move it up, right? Are you ready for that algorithm? Okay. So it's called, there's cute words for this. It's like your book calls it one thing, I call it other things. They might call it percolating. Like it's like I'm going to use the phrase bubble up. Like you're bubbling up a node, you're pushing it up, and you're having it like rise up due to how big it is, like the air in it or something. So it's called bubbling up or down, or percolating up or down. Like you're moving nodes up or down the trees to children or to parents, all right, to keep the heap property in check. Okay, so as you're putting stuff in your heap, you're gonna have things be out of order. If you change stuff, like it's just gonna happen. And when you add new things, they are not going to immediately have the heap still be a heap, of course. So you're gonna have to shuffle stuff around. So for example, you'll need to bubble up or percolate up a node that you've added or swapped out or changed if it's too large. All right, so let's say, I don't know, let's say instead of a 7 here, let's say I add a 50. Like I change that to be 50. All right, so this is no longer a max heap, right? It's no longer a max heap. What needs to be happening is like that should be true, and that should be true, and that should be true for every single line in this tree. It's called an edge. For every single edge, that should be true. It's now no longer true. This one is not happy, right? So I gotta fix it. The way you fix it is you swap. You swap this node that's bad in its current spot. You swap it with its parent. You know how to calculate the index of its parent, just like it's your index minus 1 over 2. Boop. So go find that index. See if the parent's okay. Like, no, it's not. We should be the parent. So you're going to swap the 50 and the 17. That's going to be your algorithm. You're going to keep doing that until you get up to the root, potentially. So, all right, 50 versus 17. Obviously, the 50 wins. We got 50 here now, 17 here now. And then you keep playing this game. It's like, all right, 50, let's look at the parent now. If there is a parent, I'm not at index 0 yet. I'm not the root. So 50 versus 19, yeah, the 19 deserves to, like the 50 deserves to bubble up some more. It's got more air in it. So we're going to swap 19, 50, and then you look at 50 and its parent. It's like, oh, we're good. So you stop. But your loop would go until your node that you're considering to potentially move up further, to bubble up further, is at index 0, right? Because that would be the highest place you could go. Does that algorithm make enough intuitive sense? Like you're putting it somewhere, you're changing something, or you're adding a new node. You're just going to keep looking at parents to see, like, all right, am I done yet? Is this in the right spot yet? Because now it's still a heap, right? This is for sure a heap. We've made it a heap again. Everything's happy. All the other things, like 50, because like we just put something bigger here. If this was already true for 19 and 3, for sure it's true of 50 and 3, right? It's not going to mess with anything else in other parts of the tree. It's just like, it's you versus your parents all the way up, potentially to the root, all right, if you've made a node too big, okay? Likewise, if you change a node and you've made it smaller, you may need to do the same thing, but move it down the tree. You bubble it down the tree. It's not as heavy. So it's gonna move its way down. Okay. So yeah, it doesn't have as much air. It's deflating. So yeah, if your node is small, it doesn't belong all the way up there. Let's say that instead of 19, let's change this to be 0. Like I change it to be the key 0, and now it's no longer a heap. So we'll have to put this 0 in a different spot. All right. But It's a little bit more complicated to bubble down than bubble up because you just have one parent when you're bubbling up. When you have two children when you're bubbling down. And you have to always make sure to keep it a heap. It's going to be 17 versus 3. Who are you going to put in the place of the 0 right now? You have options, right? If you put the 3 here, 3 and 0, this isn't a heap, is it, still? The 17 should have been the one who won out. You see that? So that's important. So you do have options. You have to look at both of your children, and you keep swapping with the one that's bigger, because that's the one who should be the parent now. Okay, I hope that makes sense. So that's important. So it's like 17 versus 3 now, 17 wins. So we're going to swap the 0 and the 17. Now the 0 is here. Maybe it's happy. Like if there's no more, you have to keep on checking, like, do the indices that are my children exist? Maybe there's only one of the indices. Like maybe this one didn't exist or something. You do have to be careful. Like only look at the things that are actually there. But if you got two children, it's always swap with the bigger one. So, okay, 2 versus 7. The 7 wins, so I'm swapping the 0 with the 7. That keeps it a heap correctly. Because if it was the 2 that I swapped with, it wouldn't be a heap, right? It would be in the wrong spot. So this is now a heap still. We've preserved everything. The rest of the tree is fine. Yes? Are there any questions about those algorithms? You got a node that's too big, you bubble it up. You got a node that you have a node that's too small, you're going to bubble it down just to preserve the heap property. Yeah? That's important. Yeah, there are going to be, like I was saying, there's going to be some special cases. Like when you're bubbling down, you may be done, right? Like you have to make sure you have children to look at. Same with bubbling up. Like, am I at the root? If so, there are no parents above me. I can stop now. I am the maximum, or whatever. This is a min heap example, by the way. So let's play this one just to get practice with it. So this is what's true about this. The heap property is like every parent is smaller than or equal to its children. Yeah, like that. Cool. So it's fine right now. And let's say we needed to, goodness, what could I do here? Yeah, when you're bubbling down, remember that there might be only one child node to access, first of all. Like, let me just draw an example so I can keep the one on the right clean. Like, if this is your heap, like, this one might not exist, right? If you are here, if you're looking at this node right here, and you're like, I need to bubble down, for a min heap, I'm too big. I need to keep going down. Bigger things need to go down the tree. You need to check first, like, because these are indices, right? This would be index 5. This would be index 6. Can I go to index 5? Does that one exist? You're going to check against the size of the vector, aren't you? That's how you know if that index exists. You'll notice that index 6, no, that's not there, so I can't go and look at that one, okay? So that's that one. And then, yeah, there might only be just one child node to access, but you know then that it's going to be on your left side, isn't it? If you have just one child, it's always on your left because it's a complete tree, right? There's no way that the other one would have been filled in first, okay? So, yeah, if you have 0 children as well, like once you get done, if you have 0 children, you're also done bubbling down. So let's see. Let's add, I don't know, what's a good number? Let's say I added, what could it be? Let me think of some examples real quick. What was I doing before? 8, 10, 0. Let's do an example of bubbling up. Let's say instead of a 5 here, this is a 0 now. Okay, so it's the min, and it needs to go up to the top. And so what's your algorithm going to be? You have to keep going, right? This is now 0 versus 3. The 0 wins, so I'll swap. 3, 0. This is now 0 versus 1. My parent, and you always check, like I'm at index 1 right now. I need to look at my parent. Does my parent exist? Right? It does, because I'm 1 and it's 0. That's okay. So I'll swap. So now it's 0 and 1. And now your loop needs to stop, because it's going to be a loop. Just keep looking at parents until I'm done. You are at the root now. There is no parent. Does that make sense? It's like you're going to be in a loop, and you're going to stop when you notice you don't have any parents left. All right? It's like when you bubble up, you're done when you reach the root. And when you bubble down, you got to check if your children exist, because once you hit a leaf, you're again done, right? So let's say, I don't know, do I want to do like a, maybe, let's say instead of a 6, this was a 10. Yeah, so it needs to go down the tree now. And so you're gonna notice that, oh, I'm at this node, I need to swap with the bigger of my children. Oh man, I only have one. So you need to notice, like, all right, I'm at index 2. I could look at either indices 5 or 6. Those are my children. I want to swap with the, I want to swap with the smaller one because this is a min heap. I better go and check and see, can I access index 5 and can I access index 6? There's going to be a special case where there's only just one, right? So you're gonna notice that you're in the case for that one this time. And then you're going to swap with just the one child in that case. So this is now going to be 8. This is going to be 10. All right, so that's going to be the idea. And yeah, that's how that works. So like if there's only one child to access, it's going to be on the left side because it was a complete tree. The next one would be on the right. I think that's everything that I wanted to say with a min heap this time as an example. All right. Any questions about that before I show you some code? All right, so let's take a look at just some pre-made code for Fen. So I'll copy that in for today because it's a lot of typing. It's a complicated loop it's not easy to get right. It's in your book, of course. Boop. So let's do heaps with vectors. So here we go. Here's a bubble down implementation. Let me try to walk you through it. So I've got the following heap. It's the one we're looking at here. So it's this heap. I've got this heap right here with 100, 19, 36 in this exact order, 1, 2, 7, right? Just like that. So let's say I've got, and I put, did I already do this? I don't think I did. Where was I? Yeah, let's say I've got a, we'll just stare at this one for a second. So this is the heap I've got right now, almost, but I've put a 0 here instead of a 19. All right, so I put a 0 here. This is now a 0 and not 19. All right, so that's what I've done in the code. It's a 0, and it needs to be bubbled down the tree, right? It needs to be bubbled down to go like swap with a 17, swap with a 7. Like it's going to end up right there, more or less. I hope you see that. So let's go to that code, which is this one, and we'll go from there. So, oh, sorry, I already drew it. Cool. Is this one right here. So we got the 0. It's this exact example. I wasn't looking at it because it was small. So yeah, we've got that exact example with the 0, and it needs to be bubbled down or percolated down. So you're going to pass along the way that I'm going to implement it is I'm going to give it the heap as the vector, right? Vector of ints. And I'm going to give it the index of the thing that needs to be bubbled down. All right, so that's at index 1 right now. So that's got the 0 there. Get it where it needs to go in that heap. All right, so get it where it needs to go in that heap by bubbling it down, and here's going to be the algorithm. All right, so given a vector v and a starting index of the thing that's out of place needs to be bubbled down, and this is a max heap. All right, so I'm going to make a current index variable, and then I'm going to make a loop that is going to stop eventually. I'll break out of it myself manually. All right, so I'm going to look at what I've got at my current index because the current index is going to keep changing. I'm going to move my way down the tree. All right, so that's how that's going to start. So I'm at index 1 right now. So I've got the 0, and it's going to be 0 versus the 17 and the 3. I first have to notice that those two children both exist. I have to compare against both of them if they both exist. All right, so we want to look left and right if possible. So the left index, we know the algorithm. It's your current index times 2 plus 1. And we want to see if that one even exists, all right? So if the left index does not exist, that means there's also not a right index, right? Because it was a complete tree. If there was not a left index, there's for sure not a right index. That means there's no children. And if that's the case, we'll notice that by comparing against the size, because the size tells us how many indices, right? So size minus 1 is our last possible index. So if we're size or bigger, that's where our left is. We are done. We're a leaf, stop. We are already as down far in the tree as we could possibly go. Okay? So that's going to break us out of the loop. Or if we're in the right spot, we'll break. We'll get there. All right? So, okay. If we did not break, we at least have a left child. So look at the key there. So get that number. We're also going to potentially have a right child. All right? So the right index is this one. It's one more than left. You could calculate it like that as well. we might have a right key when we're not sure. All right, so if the right index exists, we can set right key. All right, and then we'll compare against both. We want to swap with, right, if we're here. We've got 0 versus the 17 and the 3 right now. We want to swap with the bigger one, assuming we have 2 children. So here's going to be the fancy if statement, right? So we need to notice, like, all right, do we have a child? First of all, do we have a left child and a right child? We're going to compare against both of them potentially, or just the left if there's only the left. And we're going to swap with the bigger one. We are done if we're already in the right spot. Let's say that this really was like we're here and we do have 19 still. Like, does this need to bubble down any further? No. 17 versus 3, there's nothing bigger underneath us. We're done if it's already 19 or something. So let's take care of that one first. So, all right. So if the, all right, here's the if statement. It's going to be a little disgusting. All right. So if neither child is bigger, we're done. That's this if statement noticing that. All right. So if neither child is bigger, we're done. That means we are greater than or equal to them. All right. So the key that we're looking at and trying to potentially bubble down, if that is already bigger than the left key, and if there's a right index, it's also bigger than the right key. Do you see how that's combined there? It's like only if there's a right index do I care about comparing against it. So that's what goes on there, right? So if that is true, that means it's bigger than both of them, or just the one if there was only a left child, will break out. All right, we're already in the right spot in that case. Okay, so that's important. In that, if we have not stopped, all right, if we didn't break here, we have at least one child. If we didn't break here, we've got a child that's bigger than us. We need to keep moving. All right, so we have somebody bigger than us. We're still not sure which one it is yet. We want to swap with the one that's bigger, and like that's our new. We want to focus on that new index because we might have to move down even further. All right, so okay, now this is us figuring out which one is bigger. All right, so if the right index exists, if the right index does not exist, excuse me. So if the right index does not exist, or the left key is bigger than the right key, this is the case where I'm swapping with the left key. Does that make sense? This is the case where I'm swapping with the left key. That one is either bigger or the right one didn't exist. And we kept going because something was bigger than us, which means that, all right, was the left child. The left child is the one that's bigger right now. So we'll swap with the left. So we've got a current index, we've got our left key, we're going to swap by putting the left key at the current index, and then our left index gets what we were looking at. So like this is me doing this. 0 was here, the 17 was here, now it's flipped. All right, now we got 17 here, we got 0 here. That's what's going to happen with that example. And then we want to move down the tree. Now we got the 0 sitting right here. We know we're not done, right? So we got to let the loop continue in that case. In the same exact way, because we know we have to swap with that 7 eventually too. Okay, so that's how that's going to work. Potentially, you wanted to swap with the right. If this if statement was not true, this is what it means to say that the left was bigger. If that's not true, we want to swap with our right key, and also do the same thing. Right, that one was bigger. Make that our current index. That's our point of like not contention, but like. That's what we want to zoom in on. That's what we want to focus on next, because it's still, after we swapped and put the thing in this spot now, it may be the case that we're in a bad place. And so we'll swap with the right one as well. Like this one, we'll swap with the right. And notice that the 7's bigger, so we'll do the swapping with the 0 and the 7. And now we're here, right? Our current index is here. Our current key is still 0. We're always just going to keep continuing the loop as long as we have children, and one of those is bigger. So we're going to finally hit this break. It's like, oh, we don't even have a left index once we're here, so we're finished. All right. So it is a little complicated, this code, but that's what's going to break us out of the loop for this one. It may also be the case that like it's moved down far enough. Like maybe there were only, once we put this here, maybe it was like -2 and -7. We would have been done in that case. The other if statement would have fired and stopped us. Okay. So there's a bunch of different ways to be done, but I hope you kind of see how it's going to work. It's just a loop that gets the things in the right spot, taking care to notice, like, do I have children at all? Do I have just one child? I have to be very, very careful about all of those options, and it becomes a little weird looking for the if statements, but they're all necessary. Okay? So yeah, are there any questions about this code as you see it right now? I think it's going to be something to study, maybe offline. But do Do you kind of see the intuitive ideas? How do they match the words that I was saying, the text on the slides? So yeah, there's that. And then I want to show you this code running, of course. The rest of the things I have are, it's like I'm getting the parent and stuff. Like, where am I? Dun, dun, dun. I'll show you that. So like to get a parent's value, like you're going to do a bunch of these kinds of operations. We don't need that one for bubbling down, but like for bubbling up, you want the parent. Like, all right, if I'm at this index, and this is my heap, the parent's value is this one. Just go to this index, calculate it that way, go there, and then the maximum in your heap, you give me a heap. I'll tell you the maximum very quickly in constant time is the thing at index 0. If it's a max heap at least. That's quite nice. There's your constant time algorithm, all right? So yeah, let me show you this running. So we're doing the bubble down. Or the percolate down, and you're watching it work. It's like, all right, we're bubbling down. We're swapping with our left. Our current index is 1, so that's this one. We're swapping with the left, which was 17. So left and right keys were 17 and 3. We're going down the left because 17 was bigger. And then we're at index this one. We're at index this one. This is 0, 1, 2. Index 3, I see a 0, and I'm comparing against the 2 and the 7. Right? I got 2 and 7. I've got 2 keys. I'm going to swap with the right index because 7's bigger. And that's how we get our tree in the correct orientation. So it's happy. And then find max is like still 100, goes to index 0, constant time, find max. The parent value of the thing at index 3, 0, 1, 2, 3, this one, the parent value is the 17 now. That has been placed there. 17, and then the entire heap looks like this. It's 100, 17, 36, 7, 3. It's exactly this. All the way with 0 at the very last index. So it turned into the heap it needed to turn into. All right. So yeah, there's that one. And I think that's all that I wanted to say about this example. Are there any questions about it? You'll get this code. Definitely take a look at it. That's a fun little algorithm. It'll also be in your book, of course. So yeah, there's that. Let's next talk about insertion. If you want to add something, it's always like you've got a heap, a new patient, right? You're adding somebody into your heap, adding a new value. It may be in the wrong spot. So here's the algorithm for insertion. It's going to be bubbling up. So to insert a new value k, key k, let's push it to the end of the vector because that's going to force it to go in the right spot, right? It's like it's going to go there in terms of the tree and the drawing. It's going to go right there. Let's say we push 50, all right? And then so that it's going to be a leaf at that case at that point. And then you'll just bubble it up because it probably doesn't belong where it's been placed. Like it's probably not something so small, even smaller than 3. Sometimes it is, sometimes it can stay put, but like if it's 50, it needs to be bubbled up. So you're going to do your algorithm like, all right, 50 versus 3, always parents, go up the tree. So this is 50 here now, 3 is here now, 50 versus 19, we've got to swap some more still. So 50 is here now, 19 is here now, and is happy. Now 50 versus 100, 50 is in the right spot, break out of your loop. All right, so that's going to be the algorithm for insertion, and I hope that you kind of see it. All right, so let's say that we do this. We haven't talked about running time complexity yet. Here's insertion. This is a question for you. Let's discuss, and then I'll tell you my ideas. So if you could please get into peer instruction groups, say hello to one another, and please discuss this question and enter in your answer on the written nice page if you can, please. So here's my question for you. What do you think is going to be the worst case running time complexity of inserting a new value into a heap, assuming the heap right now has n elements? All right, and also we're going to do pushback on a vector, right? Assume that pushback is constant time. It is on average, or the correct word is what is that correct word? It has to do with mortgages. I've forgotten it. Excuse me. I need to know. Dun, dun, dun. But if we go to vector pushback, I'll prove it to you anyway. Complexity. Amortized. I never remember that word very easily. So it's amortized constant time, all right, over the life of the vector. So That's why it's okay to assume that. Assume that pushback is constant time. With that in mind, doing all of these operations, because you're gonna have to bubble up, right? It might be very quick, it's in the right spot, but you might have to bubble up. What's the work that's gonna be done? Can you quantify it? Does the question make sense? So yeah, try to analyze that. I'll give you a few minutes, and we'll come back and see if our intuition is good. It's going to be the worst case running time. Inserting into the heap where the first step is pushing to the end of the vector, which we will assume is a constant time operation. So that's not going to be our bottom. So that's I'm gonna have to deal with it later. All right, was that enough time to think of stuff? I'll give you another couple seconds to get your answer in. I'll respond to something on Discord real quick. Yeah, no, I can't. I cannot possibly respond to this in time. Let's see what we're thinking. Log of n plus 1, log of n, potentially linear time. Yeah, I like your ideas. Log base 2 of n even. It's going to be the case that it's going to be logarithmic. So good job if you thought of that. Let me kind of hint to you why. So, all right, if you're pushing a new node, constant time to put it there, and then you're going to swap with potentially how many nodes? You're going to move up the tree, right? You're never going to go down again. You're always going to go up. And so you were a leaf. You're kind of in the worst case. Always in this case. You have to move up. Potentially, if you're the biggest thing, you just push the new maximum. You're going to swap all the way until you get to the root, right? Swapping two things is constant time, yes? How many things potentially do you need to swap with then is the bottleneck? That's your question, right? And that's going to end up being the height of the tree, right? You might have to move up the entire height of the tree. Did we see that? Constant time to push, constant time to do one swap. How many swappings might we have to do where the new max, in the worst case where the new max, we're swapping all the way up until the root, we're swapping with the height of the tree nodes. Yes? That's going to be the idea. So O of H, I guess, is an answer that we could provide here. But we have a better idea than that, don't we? We have that. So like you put, I don't know, instead of this, maybe it was 101 or something. It goes all the way up. It goes all the way up in that case. Height of the tree. But we know that because the tree is balanced, we get logarithmic height out of that deal. All right, so here's the analysis there of insertion. So you add something to the vector, constant time, and then the bubble up process is you're going to look at most height of the tree nodes, right, where h is the height. And that, but, right, the height is proportional to log base 2 of n because it's a balanced tree. And every time you do a swap, it's just constant time. So it's this times this for the bubble up process, right? Plus this to do the initial adding to the vector. So that's pretty much it. That becomes big O of log base 2 of n. When people write big O of log of stuff, they actually they usually get rid of the subscript. They just say big O of a log of n. And here's why. Because any base of a logarithm can be turned into any other base of a logarithm by the appropriate multiplication by a constant. That's the reason. So like log base 2 of x is, you know that you can do a conversion, right? It's the same as log base 10 of x multiplied by some conversion constant. So because it's just up to a constant different, big O kind of takes care of that already. So it's like log base whatever you would like of n. Does not matter. But for us, base 2 is a useful one for computer science. But most people, because of this, they just write big O of log of n, because the base doesn't really matter because of the way big O works, if that makes any sense at all. So we got that analysis. Yeah, so insertion, we want to be able to do insertion. We should also want to do removal, getting rid of a node from the heap. And this is going to cause us to want to be able to bubble down things, all right? So here's how removal works. For a heap, it's always going to be, give me the max, or give me the min right now. And then I don't care about the thing anymore. Give me the new max. Give me the new min after getting rid of it. So it's always going to be removing the root. All right. So that's how heaps are going to work. That's how we're going to make them happy. So usually we're only going to ever care about removing the root. And yeah, though the algorithm I'm about to give you could work for any node. If you really wanted to get rid of like the 17 node, what I'm about to tell you will work. But usually in a heap, it's just kind of you get rid of the root. Okay, so that one only, but it's okay either way. So here, let's say we would like to get rid of an arbitrary node. Let's say we want to get rid of, gosh, well, who could it be? What's a good node to get rid of? Let me think about this. Let's say I want to get rid of this node. This 19 node. I'd like it to go away, please. All right. So 19, I'd like to be gone. So here's the algorithm. To get rid of the 19, it could have been the root as well. But what you'll do is you're going to swap it. You're going to turn it in just like we did for binary search trees. You're going to swap it with a node that's easier to get rid of. It's kind of fun to think about. Because like this one has some children. Like you can't just like chop it off because it's an array, right? It's a vector. You need all of those things in the right place. So what we're going to do is we're going to move this down to here. You're going to swap it with the last node, which is your bottommost rightmost node, the last index possibly, which is this guy, the 7. All right, you're going to swap it, and the 7's easy to get rid of. Like, or the node in that location is easy to get rid of. It'll just pop back the vector at that point. So you're going to put the 19 right here. I'm going to put the 19 right there and put the 7 here, all right? Really, you don't have to worry about putting the 19 here because you're about to get rid of it. Just like make sure the 7 is there for sure. Because what you're about to do is pop back the vector and get rid of this index. Does that make sense? So that's where the thing you don't care about anymore is. But you've put the 7 now in a weird spot. That's the only thing. It keeps the tree in order, intact, if you do it this way. But now this new node that you put, the new value that you put in the place of the node you don't want anymore, is now probably not in the right spot. So yeah, that's what you do. So you're going to swap, then you're going to shrink the size of the tree by 1. So you're going to pop back the vector, get rid of that last index. We don't care about it anymore. That now holds the thing we didn't want. So now the tree has only the numbers I want in it now, but they're just in the wrong spot maybe. All right. So the last piece of this puzzle is get this 7 where it belongs, and it's going to be a bubble down because it was something small. Something lower in the tree got moved up, probably does not belong there. It needs to be lowered again. All right. So you're going to bubble it down, the node of this index. So you're going to look and do that algorithm. All right, I've got 17 versus 3. The 17 wins, so I'll swap the 17 with the 7. And then I'm at this node. I don't have anything to the right of me anymore. I have 7 and just 2, and now the 7's in the right spot. So I can be done. Does that idea make sense to us? That's the only way to keep the tree in order, because like this is the only index you can safely really get rid of. You can't get rid of index 2, index 1 from a vector and just use all the others, right? So you had to turn it into a problem that could work for a vector. It's like getting rid of the last index is fine. So like do the swapping, move this thing that is supposed to still be here where it belongs now. Okay, so that's how that works. That's going to be your removal algorithm. All right. So are there any questions about that? Does that make enough sense? It's removal. So you swap with the last index in the place that you want to get rid of, and then you bubble it down to where it needs to go. All right. So with that in mind, I got another question for you. Try it again. Dun, dun, dun. So if you're already on the page shouldn't take much more time. It's going to be very similar to insertion, the idea, but please refresh the written nice page if you're already on it so that we can add more things to it. But here's your next question. So all right, assuming that pop back on a vector is constant time, because that's part of this, what's going to be the running time for heap removal if the heap has n things? Give that a try. Is it going to be similar to insertion? Is it different now? Because it's bubble down. Like, how does bubble down work? Is that going to be more complicated? I mean, you've seen the code. How does that change things? Maybe and you can say just h for the height of the tree. You need to worry about that. But you can replace that with log base 2 then. If you need it. All right, it should be very similar ideas. So give you another few seconds to get something in. Let's see what we're thinking. How does our analysis look? We are all across the board agreeing, even O of h, that becomes log of n. Look at us without using base 2. Nice. It's going to be that. Good. Let's talk about it. So, worst case, you're removing the root, right? Worst case, you're getting rid of the root and you're bubbling down potentially to a leaf. You got to go all the way down to a node that is your leaf. It may seem, you do maybe have a little bit more work. It may seem like, oh, do I have like linear amounts of work now? Because I always have to look at 2 children rather than just 1 parent for the other direction. But it's going to end up being okay, all right? So you are going to swap, right? You're going to look at your 2 children at every node. It's like, pretend we are at the perspective of, like, at the granularity of, like, here I am. I'm trying to bubble down right here right now. If I'm at a current node, how complex is it to bubble down to the next level? That's what I want you to think about right now. It's, you go and look and see, do I have 2 children? If so, get their values, compare if statements. You only have a constant number of children, right? Potentially 2, maybe less. And then you're going to swap with one of them, the one that's bigger for a max heap. And so that entire process of bubbling down from the perspective of one, you're at one node right now, you're bubbling down one level. Do you see how that's going to be constant time? You have maybe 2 children to look at. That's still a constant number of things to look at, compare against, do if statements about, and then do a swap with the bigger one. That's all going to be constant time per level, okay? So yeah, swapping nodes is constant time. Popping back the vector is constant time. To bubble down from at a node, you're going to do some if statements and some swaps, and so that's all constant, all right? So in the worst case, you have to swap down the height of the tree because you remove the root or something, or you swap something very small, you put it very, very high up the tree, you got to move it all the way down to a leaf, maybe. Another leaf this time. And go from there, all right? So yeah, you're going to swap down potentially the height of the tree. Hopefully you see that in the worst case, for the root down to another leaf. And yeah, because your tree is balanced, your height is proportional to log base 2 of n. You're doing constant work per node you're looking at as you're moving down the levels, as you're doing your bubbling down. And so that means in total, you're doing log base 2 of n work. Any questions about that? Do you see it? Even though there's slightly more work to do because you have 2 children, it's still a constant number of things to look at and compare against and mess with. All right? So that's going to be how that works. All right. So if we're good with that, I have just a couple more things for this set of slides, and then I have a fun lesson that's meant for like lab time, and so I'm excited. So we know what a heap data structure can do now. We want to package up the things that it's good at in terms of an ADT. That's always been our goal, all right? So it's called a priority queue, all right? So you've seen this in C++ land. A priority queue is almost always implemented with a heap, though you know that all of these operations, find the max, get rid of the max. You could implement in some weird way with some other data structure, as long as you keep all the operations working correctly. But you're always going to want to use a heap, most likely. Here are the operations on a priority queue abstract data type, right? So you think of it as like a queue with priority, like things that are more higher priority get moved to the front. And you implement it with a heap. So here are the operations. Because we call it priority queue, there's pushing and popping involved. So push, you push a value that inserts a new node into your heap with that key. Popping gets rid of the root, which is your max or your min. You could peek and see like what is the thing that is the max or the min in my heap right now. It's looking at the thing you care about, right? It's like the front of your queue. It's a priority queue though, ordered in priority order. Seeing if it's empty, getting the number of things that are in the heap, get length. So that's a very normal sounding ADT, I hope you see. And so it's a little bit different than a normal queue, but like you can draw it like a normal queue. Like, all right, you got an empty queue, empty priority queue. You can push stuff to it, like push 42. You're going to implement it on the back end with a heap. So 42 is what it has in there. If you push another thing, like push 88 or something, then now it's not going to the end like a normal queue. It's going to be at the front, right? 88, 42. Like that's how you can draw it. It's like, all right, now when I pop or peak, I'm getting out the highest priority thing if it's a max thing. Maximum priority here. All right. So I hope that makes sense. So that's just us turning the heap into an ADT. These are the operations that you could define it with. I hope you see that you'd want to use a heap to implement it, but you could use something completely different as long as you follow all these rules. Yeah. It's defined. ADT is always defined in terms of its operations. There's usually one good data structure that you'd want to use for it. Okay? So that's the goal. Yeah. Any questions about that? So yeah, one day you'll implement it. So if we're good, I have a completely different thing to talk about. Are we ready for that completely different thing? It's like a lab time lesson. So I'd like to teach you guys about Git and GitHub if you have not been like introduced to them yourself yet. You haven't tried to learn. I got some other slides for that, so I'm excited. So this might take a little bit, like pretend this is lab time now. I want to teach you guys about the version control system called Git. It's a wonderful thing, and yeah, it helps you collaborate. Like in the real world, in industry, Git is it's a version control system that's pretty much, it's one out. There's a bunch of different ones that let you keep track of the changes that you've made to your code and help you work on it with other people. This one's pretty much one out. There are others though. So yeah, if you would like to follow along, I'm gonna go quickly, but I think it would be in your best interest to have a GitHub account. Eventually, you might as well just go make one right now if you don't have one yet. It's a website called GitHub. It lets you host. They're called repositories of your code and keep track of things. It's like Google Drive or Dropbox or whatever Microsoft's version is. OneDrive for your code. That's what Git is all about, and GitHub is a way to host that on the cloud. All right. So I'm going to say a lot of new words, and I'm not going to really like test you on this or anything. This is like, just come back to the slides if you need to. This is just for your knowledge, because one day you're going to be asked to work collaboratively, and like you're going to need to know this in industry. You're going to have to keep trying it, right? Keep using it until you get it. So I guess that was a pun. So here's what Git is. Go look it up on Wikipedia. It is a version control system. It was made by the dude who made the Linux kernel, so a very popular man, Linus Torvalds, wonderful Finnish man. And it is like this, right? It's Dropbox, Google Drive, OneDrive for your code, but better because it's optimized for that kind of stuff, okay? So what it does is it kind of looks like this. You have a bunch of different lines of you doing work, a bunch of different versions of your code, like a bunch of different universes. They're called branches. Like you can branch off. There's always a main branch or a master branch, people say, master or main. People have, they call them one or the other. And yeah, it's going to track your changes whenever you say it. Like you always tell Git, like, hey, I've made some changes now. I want to, it's called commit those changes. I want you to know that this is a good version, that I care about remembering the state of the world at this particular time. And that is called, that's your change. Like you're keeping track of those changes right now. If you make some more changes, only when you say, Git, I want you to remember this, does it notice your changes and save them away. So you have to be proactive in that sense. You tell it when you want things saved. And yeah, what I'm going to do is I'm going to make a folder called F25 CSCI 41 Git demo. So it's what you do is you're going to make, essentially, you're going to have Git keep track of the changes that you've made for a particular folder. And this will be the folder that I'll use. Okay? So I'm going to make a new folder called that. I'll just make it in my home directory, I guess. So I'll say this. I will say, what is it? F25 CSCI 41 Git demo. All right, so this is a new folder. F25, there it is. Here I am inside of it. It's empty right now. And the idea of Git is I'm going to track the changes to all the files that I eventually make in this folder. That's going to be my Git repository. So you can have it at whatever level you want, but it's always some directory that you're keeping track of, some folder, right? And this will be the outer folder for me. F25 CSCI 41 Git demo, all right? So the very first thing you do, Git is a command line command. So you say Git space some stuff. And you can look at the man page, man Git. You can see what it does, like all your options. It's a very long man page. A bunch of different things you can do. I'll teach you some of them. There's way more than what I'll show you. But to tell Git, like, this is a brand new repository where I want you to track my changes, you say Git init. Hit enter. All right, that's what it does. It says some things. And notice that my terminal is kind of cool. It changed. And notice like, all right, I was just in a folder. Now I'm in a folder that's tracked by Git, and I'm in this branch. It's called master by default. So it noticed. It's actually keeping track of your changes in a secret hidden folder called .git. If you do ls, it doesn't show it to you, but ls-a shows you hidden folders, things that start with dots. So it made that, and that's where it's going to store its stuff. So don't go making that folder yourself. So that's how that works. It's the one name you can't use. And so yeah, in Git, there's a concept of like where you are. You can branch off and do some work that is maybe unsafe or something, like you go off and do something else. There's always one default branch where you're supposed to put the good stuff. You call it master or main or something, and you can branch off from that, do some work, and then you can merge it back in to the good branch where you keep track of things that are like ready to go. And that's how you can collaborate as well. Like somebody gets the code from here, they do their work, and they add it back in. They add it back into the place where everybody sees things. Okay, that's how it works. So yeah, what do I want to do? So you can branch off. So the default branch is called master right now. There are some people who don't like that word, and so they want it to be called main instead. This is what the warning's saying. So like you can change that. It'll be changed in a second when I push it to GitHub. But yeah. Sometimes if you're just working alone, the master branch is like you're storing all the different chunks of changes that you've made. Like that's probably good enough for you. Okay. But if you work collaboratively, usually you're going to want to make a bunch of different branches and like go off, do stuff, and bring it back in later. Okay. So yeah, that's how that works. And you can always ask Git, have you noticed any changes? Like what has not happened? What do you know about that I've done since I last told you to track the changes? All right. Or since I've made a change that I've told you to remember. And that's Git status. You say Git status. So Git init makes a new Git repository. Git status says, hey Git, tell me what's going on. What do I see right now? It's like, all right, you're in this branch. You have not committed anything at all, so I know nothing about this folder. And there's actually nothing for me to even notice right now. So go make some files and tell me about them. That's what it's saying right now. All right. So I use Git for code from class, and like here I'm in my default branch, and it's called main for this one instead of master. So cool. So let me add a text file, and we'll see how Git status does its stuff. So here I am. I'll make a new file. I'll call it hello.txt. Let's say hello world. I'll save it. Let me go to this folder in here. F25. There it is. So here I'm in the folder. So I've made this new file. Here it is, hello.txt. Oops. So I've got this file. I can ask Git, hey, Git status now. It's like, ooh, untracked files. It noticed that I've made a change to this directory it was watching. And it's like, all right, I'm not keeping track of this file yet. If this is a file you really care about, that's important to you, you can tell me about it by saying git add, the name of it, to include that, and I'll add it to my next commit when you're ready for that. So it notices your changes. It knows that there's a new file here that it doesn't know if you want to keep track of it or not, because maybe it was like a temporary file. It's up to you if you want Git to keep track of that. Like for example, you're not going to want to commit your compiled files. You just want to commit the code. I'm lazy when we do our code from class. You shouldn't be doing that. So that's how that works. And so yeah, you want to tell it like, that's a file I care about. Keep track of it for me, please. And so that's what git add does. All right, so Git notices your changes, and if you want to save them, you stage them. You get them all ready, because maybe you have multiple files that you want to keep track of all at once. Like I made 3 files and I changed them or whatever. Add them all as one chunk to the next change tracking thing. You call stage them. You put them on the stage, have them do a show, and then you commit them. All right, so it's a 2-step process. So if you want to stage a file to add it to your next thing called a commit, and a commit is one of these circles here. It's like a chunk of things that you want to keep track of, like that universe, that state of time in your code. That's what a commit is. So we want to do that. So you say git add, the name of the file you'd like to keep track of now. So I'm going to say git add, or here, I'll do it up here. Git status tells me all this. And I can say git add, the name of the file I wanted to keep track of, or the one that if I've changed it, like add that to the next commit. So git add that. Alternatively, you can just say add all the files that I've made changes to in the following directory. You could have said git add dot, because a dot is a shorthand for the current directory. So you say git add space dot, and that will just put into the staging area all of the files that you've changed. Git add dot would have added everything. So either way, it's fine. And now if I say git status, it's like, ooh, changes to be committed when you're ready. These are the ones you're telling me to keep track of to add to the next chunk of stuff I care about to remember. I could have made other changes and they would all appear, but I just got the one right now. All right, so this is a brand new file to me, hello.txt. If that was a mistake, you can do this, but no, I want to keep track of that one, please. And so if you want to commit the changes, it's not yet committed, Git still doesn't know about it yet fully. It's like we're getting ready. This is the next chunk. We're creating the chunk, and you say git commit, right? Git space commit. Commit this change for me, git. And what it does is it opens up the default editor, which is unfortunately nano, on your terminal. You can change that. And what you do is you're supposed to write a commit message, give as many lines as you need. The first line will be the header of it, but describe your change. It's call it whatever you want. What do I want to say? I'll say, I don't know, call it this is my initial commit or something. Done. Initial commit. I added hello.txt to this file. That's what I did. And you can save and quit out of your editor. Go to whatever default file name it gave you there. And it's all right, it's happy. If you ask for git status now, it will show you that we're good, nothing to commit. It's remembered. It has remembered. So if you don't want it to open up your editor, you can say git commit -m and give between quotes your commit message is what it's called. All right. It's just something that describes your change that you've just made. So when you come back next month, you'll remember why you told it to keep track of that particular universe, that particular state of your files. All right. So that's what a commit is all about. Are there any questions so far? You're going to see what it's doing? Just all right, you got some files, you made some changes, you tell Git, okay, these changes now I care about. The universe right now of this folder, save that so I can potentially come back to it if I need to. That's the goal. All right? You have all the versions that you could rewind back to if you need to. So, yeah, if you want to see what's going on in my branch, you can say git status, it's going to show you that you're done. Git log shows you all of the commit history. So git log. Show me the log of everything. There's just one right now. So there's always a number associated. It's actually a hash. It's a hash value in hexadecimal associated with the files of your commit. This is commit number this. And this is where the master branch is looking right now, but you can tell it somewhere else if you have more. And this is the date, the author. This is my initial commit. I added this file. And so this is the state of the world as Git knows it. It knows about everything that was there in that time. All right? And so, yeah, kind of the goal is, let me make some more changes. We'll notice those changes, and we'll go from there. Let me show that to you. So I got this file, hello.txt. Let's mess with it. Add another line, another line, dot, dot, dot. And then I'll also, in addition to that, let's make a new file. Let's be I don't know, blah.txt. Another file. Wow. So now I got two files in this folder. If I say git status right now, I don't know the best way to show this to you. There's my two files. Git status. It's ooh, a file that you've told me to keep track of, you've modified. And I also have noticed a new file. Would you like me to track that one too? Yes, I would. So I can say git add and give the two files separately, or I can say git add dot, add all the changes to my staging area. I want to keep track of the changes that I've just made as well as this new file. Add everything to the next commit, please. Everything in this folder. So git add dot, just add everything in my current folder. Git status shows now that, all right, if you would like to commit, what I'm ready to commit is the fact that you've made this new file, and then also you've modified hello.txt in this new way. And so that's the next chunk that I want it to remember, so I can commit those changes. All right, so I can say git commit, and also just say -m this time. -m, and here's my commit message. I'll say, I don't know, made some changes. Something like that. And so it knows. And now if I say git log, it's remembered The state of the world used to be like this. If you want to go back to that, you can. You'll have it forget about that file and all that. But you can also have this one. This is where you are right now. With these new changes, it's got a new number associated with it that you could rewind or fast forward to. Does that make enough sense? Like, those are the chunks of the state of the folder that I told Git to remember. I can always go back to them. Okay? I'll show that to you in a second. But that's the idea. Okay? So there's that. Let's see here. Usually, what's going to happen is you're going to want to make a bunch of branches. So like, you've got your master branch so far. Like, I made this initial change. I've gone and made this other change. Eventually, you're going to want to be able to do something like this. This is your master branch. You want to go off and like give this to somebody or have somebody else work on it. Let's say that like I give this code to my cat and like I have them go work on it and try some stuff. Like, you can make another branch called Lonzo. That's the name of my cat. You can base it off of, that's called branching. You can base it off of an old commit from another branch. Like, branch off from this one that I've just made and maybe make some changes. Commit over here to Lonzo's branch. Maybe there's some other changes happening under the hood to master. When Lonzo's ready, he can merge it back. Merge his one change back. Maybe some change you'll have to like resolve some conflicts. We'll get into that. But like, that's how it could work, and you can go on from there. So like, you can branch off from a state of the files, make some changes, and then merge them back into the main line where everybody's looking at stuff. Does that idea make enough sense? That's how it works. All right. So that's how you'd work on a project. You probably make a branch for you, a branch for your partner, and then leave the master branch for when you're ready to, like, you got something working, put it back in. All right. So the way to make branches is you say git branch and then some stuff. So let's make a new branch called Lonzo. So I'll say git branch Lonzo. And it's always from where you are. So I'm in this, like I made this last change to master. I can branch off from where I am right now by saying git branch, give the name, Lonzo. All right. So that has made the branch, but has not switched me into the branch. See that my terminal still looks like this. Git status says I'm on branch master still, but I've made the new one. That makes the new one. And then you can say, if you say git branch by itself, that shows you the branches you could go to. Right now I'm in master, but I could be in this one. All right. The way you get there is you switch. You say git switch into this branch name, please. So git switch into Lonzo. So now I'm in the Lonzo branch. My terminal is cool enough to tell me that. And if I say git log right now, you can see that I'm also in this state of the world in Lonzo. So like master and Lonzo, they're pointing here. It's like a pointer, essentially. It really is. To that state of the file. To the state of that folder's files. Okay. So now let's say that Lonzo's going to do some work. Go make some changes. What does Lonzo want to do? I don't know. Let's change, like, so I'm in the Lonzo branch. Let's change blah. We'll do, like, I'll add another line. Da-da-da. So I made some changes to the Lonzo branch. Let's commit that change. All right. So there I am. I'll say git status. Like, okay, I've modified blah.txt from the Lonzo branch, on branch Lonzo. So I'll add that to be changed. So I'll say git add. I can say blah.txt to add that change, or I can just say like git add all the changes in this current directory. Dot. Git status now shows that you're ready to commit that change to this file blah.txt. I can say git commit -m. I don't know, changed. Give some description. Change blah.txt from the Lonzo branch. Boop. So just like that. So that's where Lonzo is right now. If I say git log, you'll notice that I'm in a new place. Lonzo's over here, but the master branch doesn't know about that yet. It's still sitting right there. You see that? So it's remembered all these states of these files. And you can move around between them if you need to. All right? So I've done it. I also want to show you git diff. I'll show you that in a second. Let's go back. We can go back to master. So here I am, blah.txt. If I print out the file, cat is a program that just like prints the file to the screen. So that's what blah looks like from Lonzo. If I git switch back to master, still got the same files, but if I look at blah.txt, it doesn't have the change. That's very powerful. Do you see that? That's quite nice. So you can go be brave in Lonzo's branch. You can merge it back if you need to. All right. So that's how that works. And yeah, so now I'm back in master. What do we want to do in master? Goodness. Let me do something unfortunate. Let's change blah.txt in master now. Let's be like, all right, dun, dun, dun. I'll add another line. I'll say a new line at the start. Bunch of exclamation points. Okay, so I'll do that. Get status. There's a change. Let me commit that change. Get add blah.txt or get add dot. Status shows me that I want that to be tracked. Git commit -m. I changed blah.txt in master. Or actually, before I do that, let me show you git diff. Git diff shows you the difference between like what it shows you your changes essentially to each file. Git diff shows you what has changed. I think I have to unstage that real quick. Let me do exactly what it says if I want to unstage it, but not. I don't want to get rid of my changes, but I just don't want to put them in the thing. Right now, I'll restage it. So there, I've modified blah. It's not in my staging area right now. If I say git diff right now, it will tell me the difference between the files that it knows about in terms of the last commit and what I've changed. So you see what looks a whole lot like the auto grader. It showed that, like the way you read this, it's called a diff. It's short for difference. It's like, all right, in blah.txt, there is this thing. That's the change that you've made. It would show things in red if you got rid of stuff. Like that's showing you all the changes that you've made that it's noticed of the files that you've told it to track. So yeah, let's add that now. Git commit -m. So I changed blah.txt in master. All right. So now I've got some differing versions of blah.txt, don't I? I've got one that's in Lonzo. So now we're safe. Everybody's happy in master. Blah.txt looks like this in master. If I switch back to Lonzo branch and I look at blah.txt, those files are different. Oh no. But that's how programming works in large groups. So what we're going to have to do is resolve that. All right. So the way that this happens is, gosh, how do I want to do this? That should be fine again. What I want to do is I want to merge. All right. So I've got two changes to the same file. I would like to merge back in the change, like it's essentially this is what's happened, right? I made a change in master, I'm here. I made a change in Lonzo, I'm here. The state of the world is slightly different. Bring it all back together. All right, reconcile the changes. That's called a merge. So the first step is get where you want to merge into. So usually you want to merge into the master branch. So I'm going to get switch back to master. So I'm in my master branch and get log. I've got some changes in master that this is what master knows about, of course. Has no clue of what's going on in Lonzo yet. But we can bring Lonzo in by saying get merge from Lonzo. All right, get merge Lonzo. You hit enter and it brings you into the editor again, like describe the merge process that's happening right now. Like, what did you do? Like, what's happening? What happened from Lonzo? So, like, it's going to add it as a commit, those changes that it's merging in. So I'll just keep it the default merge branch Lonzo. That sounds fine to me. Save. And it was actually able to do the merge, even though the files were different. Because usually, like, you're working on somebody's working on one function, somebody's working on a different function or something. Like, as long as you're not working on the same function, as long as I wasn't working on the different lines of the file, the same line of the file, it's happy. More or less happy. There was no conflict. It's able to get log, like I merged branch Lonzo in, and it was able to reconcile the changes. So if I look at blah.txt now, it kept my line from the main branch, master branch. It also kept the line from Lonzo's branch. Does that make sense? That's kind of neat. So yeah, that's most of what I wanted to show you. Sometimes there's going to be merge conflicts. So let's go back to the Lonzo branch. Let me introduce a merge conflict. All right, so let's change. Let's change the blah file again from Lonzo. So I've got. Let's take this. Let's see this file, and I'll be like changed in Lonzo. All right, I'll do that. And then I'll make a similar change to that line again, right? I'll make a similar change to that line again in the main master branch. Then there's going to be a conflict. It's line-based usually in Git. That's what you tell it to by default. Switch back to master, and let's look at blah as well. Oh, shoot, I have to commit that change. Excuse me. So it's telling me, oh, you've made a change. Don't switch until you've committed it. Thank you. Aborting. Good job. So let's get status. Shows me that I've modified something. Git add the thing, add the change. You don't have to keep saying git status. I'm just showing it to you, so to show you how it would change. You could have just said git add, git commit, -m, changed blah again in Lonzo. Boop. And then I can switch back to master. So this is what the log says for Lonzo. It's like changed. Like, it doesn't actually know that I've merged things back from the master branch. It's fine. Git switch back to master. So I'm in master. I've got blah.txt. That was that resolved thing. And let's make another change. Which line was it? Let's do change blah again in master. It was this line, right? It's changed in master. All right. So there I made the change there. Let's commit that change. So git add dot, git commit -m, changed blah again in master. Cool. So I've made that change. This is what blah looks like for master. This is what blah looks like from Lonzo. So this line, the same line, now has a conflicting change. All right. So let's get back into master. Let's try to merge again. Git merge from Lonzo into me. And then it's going to be like, ooh, merge conflicts. Could not merge automatically. Fix the conflicts. And then we're good to go. If you say git status right now, it's like it's telling you like, oh no, unmerged things. Go look at blah.txt, fix it. Because it needs a human. Boop. And so here's what it's going to show you when you have conflicting changes. It's going to tell you, it's going to look like this is a little weird. These arrows mean file thing on the left. That's going to be the branch you were merging into. And these, it's like arrows pointing to the right. It's like the other branch, Lonzo. It's like this is the conflict right here. This is what it's saying. I see in the left file, and it's got these equal signs to separate the differences. So it's saying that, all right, in this file, in master, where master is right now, it's got this versions of these lines. And this last line was not part of any conflicts. Like, all right, they all agreed on that line. Okay, they're happy with that. These are the changes, all right? So these are the differences. So master has these. Lonzo has that one. What do you want? It's the human's job to fix it now, right? So that's what we want. And so what we'll do is I don't know, do we want to keep them both? Like we have to decide. We have to decide what we would like right now. And so, I don't know, we'll keep them both. Why not? Dun, dun, dun. And so you get rid of all those other things. Like this is the file itself still. Like, okay, let's have both lines be there. That's one way to resolve, right? So now if you say git status, it's again, says both modified. I've resolved the conflict. Let's add it to the commit. All right, git commit or git add blah.txt or dot git status. It's saying like, okay, we're ready. Conflicts are fixed, but you are still in the process of merging. Don't forget that's what you were trying to do this whole time. I was trying to be helpful there. That's good. So git commit. And it still does have, like, by default, it has the same merge name there. Merge commit message. It's like, yeah, that's what I want. Cool. Control X to save. It's like merge branch Lonzo. We are good. Okay, so git status now shows that I'm on branch master. I got nothing to commit. Everything's fine. Everybody's happy. And git log shows me all of the changes that have ever happened, essentially, because everything's been merged back into master at this point. So it's showing like this is where the Lonzo branch is. You know about that commit now in master. And you also did some other things. You changed blah again after that, and you merged Lonzo back into you. So there's a lot of different things that have happened in the master branch so far. Okay? Are there any questions about that? And you can always get back to where you were. Do I want to show that to you? It's git checkout. If you want to move around, you say git checkout, and then you give like a number. So if I wanted to go just for a split second, take a look at the state of the world, like at the very beginning of time, go to the log, find the commit number for the initial commit or whatever, wherever you want to go and look at for a split second, because it's remembered where you are, where you've been. So like if I take that number and I say git checkout, it's nice that like if you press tab, it does that. Check out these branches. Checkout. Boop. If I hit enter, you are now in detached heads. It's like you're doing something weird. Remember that you're in a weird spot right now. You're in a weird place. It's like I'm at a specific commit right now, not at any place where a branch is. You can always you can go back to where you were by saying git switch dash is what it's saying there. That's nice. So like here's the state of the world. See that other file wasn't there yet? It remembered that. This is what things look like. Here's hello.txt. Hello.txt. It was just the hello world. It's just the one file in that initial commit. So it's remembered the state of the world. You can always go back to those different states that you've made commits about. That's the beauty of Git. It's tracked all of those things. You always go back. It was git switch dash to get back to where we were. All right. Git switch dash to get back to where we were with those new files. Here's what hello.txt looks like right now. So you can always move back, rewind, fast forward. You got all these branches. You can branch off, merge back. And that's pretty much software engineering with version control. Does that make enough sense? A lot of new words, a lot of new ideas, but I hope you see it. It's very cool, very nice. So after git checkout, and then you say git switch dash to go back. All right. To return. Something like that. So yeah, that's Git in a nutshell. Git tracks your changes. GitHub is a place where you can host on the cloud your Git repository. So GitHub is just a website. Most open source projects are on GitHub. You can put all your code there if you want, but please, I will give you zeros if I find any of your code publicly available on GitHub. You can always make a private repository, and that's what you should be making for this class. Git and GitHub are great ways to share code with your partners if you're working in partners on labs. But please remember to be making private repositories on GitHub. So otherwise everybody could see it. And I work very hard on these labs. It's hard to make new ones. So yeah, that's what I wanted to say. Let me show that to you. I'll make a new private GitHub repository in my account, and I'll push it. It's called pushing it to the cloud. Push the one I've made. So yeah, I'll go to GitHub. Do I have to log in? We will see. Of course I do. Sign in. Sign in. Sure. What does it mean? Oh, it's not very useful anyway. Okay, fine. Boop. Connect. Continue. Two-factor authentication. Yay. Cool. So here I'm in my GitHub account. I can make a new repository. Say new. And what I want to call it, I'll call it the same name as this one, F25 CSCI 41 Git demo. Dun, dun, dun. You give it a description if you want. Visibility, private. Everybody's noticed me clicking that, right? That's what you are going to click if you make anything for this class. All right? And you can just make it default. Don't do anything. I've already got a repository on my terminal that I'm going to put into here. All right? That's what I'm going to do. All right? So private, create repository. It's got the name under my account. And then it's like, you scroll down, it's like, oh, I have an existing repository on my command line. Here's what I can do to add it. All right. There's a bunch of different ways to add it, by the way. Dun, dun, dun. You can do it with HTTPS or SSH. I'm going to do it with SSH. I'll have to show you some stuff. You'll have to read the documentation. The way that you connect and push things from the command line with HTTPS, that's probably the easiest way, is you have to set up a separate password for GitHub. It's going to make you log in with your username and that new password that you've made that's not the same. It doesn't have to be the same as your account's password. It's like a pushing password. So you can do that, or you can upload what's called an SSH key, which is something that I have done. So I'm going to follow that. I'm going to click SSH, but probably the easiest way to do it is like follow a tutorial somewhere to push to GitHub using HTTPS. There's a lot of stuff that you have to do first. But yeah, either way, it's essentially giving it a URL to remember. It's like get remote at origin this. You just follow all these things. Get remote at do that. GitHub subscribes to the idea that the default branch should be called main rather than master. And so just the thing that it's telling me to do right now is like rename your branch right now to main. So it's just renamed master into main right now. If I reload the files, it did that for me. And then you say push to, they've called it origin, push to the cloud, my current branch. So you can push that. You can do it that, and then if I refresh the page now after I've pushed, you can see all the changes. You can click on see the current versions of the files, like you've gone to these pages already, but you can also look at all the commits. Click the commits. Here they all are. You can see the diffs for all of them, like here's what happened in that change right there. You can go click on that commit to see the files at that point in time. You like click view commit details or whatever. Here's the file at that point in time. Go there. I want to see that version of it, please. I guess it's here. View file at that version of time. That's kind of neat from that thing. So you got that one. By default, it only pushes the main branch. I go back to that main, which was your default master branch. It renamed it for you. If you didn't do that line, I would have kept it called master. And if you want to have the other one, you gotta switch to it. Switch to Lonzo git push. And then it's going to tell you like, oh, I don't know about this branch. Like, do this to make it know about it. It's like, there you go. Do that. And now I put Lonzo. If I refresh the page, now I can click here and look at also the Lonzo branch. So sometimes branches are very quick and you want to just like do a change, like a change for this bug, merge it back in, and then you want to delete that branch and do it all over again for a different change. So for long-lived branches, you can push them to, it's called pushing to GitHub. If you don't want them, you don't push it. You just keep it all in your main branch. So now it's called main. Cool. Yeah, I think that's most of what I wanted to say. Yeah, and that's what I've done. And I'll get that for you. So the metaphor is, how do I want to say this? The metaphor is you've got your repository on your terminal. You've used the git command to do that. And then you've uploaded it to the cloud on GitHub. And the way that you did that upload was called a push. You pushed it to the cloud. If you want to get, and if like you've been working with somebody, you got a partner, and they've made some changes and they push it to the cloud onto GitHub, but you don't have those changes, you pull them. You pull them down. That's the metaphor. So you say git pull to get changes. Pull down, please. Just like I said, git push to get stuff. So let me show you how to push a change, and we'll go from there. So I'll do, I don't know, let's change hello.txt for a change. Let's say then hello.txt. I'll say, I don't know, another line after that. Ta-da. So I made a change. Status, git add dot, git status, git commit. I don't know, changed hello.txt. So now I've got a git status. It's like your branch is ahead of the cloud by one commit. You can push that change. You've committed it. I know about it on the terminal, but the cloud does not know about it. So you can say git push to push that change. So it didn't know about that before. It still says it had the old hello.txt with the made some changes commit. That was the last one. But I refreshed the page. Now it's like, oh, this version is from the change hello.txt file. You committed just now that thing. You can look at the current version and also rewind, see the history of the file with this history button. Show you all the commits that messed with that one. So it's very useful. I hope you see that. And that's how you can give code to people. If you want, like, if you're going to work in a pair, you make a private repository, repo for short, on GitHub. One of you pushes your code, and then somebody else needs to pull it for the first time. To pull it for the first time, that's not called pull. So to pull, for the first time, you say git clone. That's how you pull it for the very first time. Then you say pull after that once you got it. And then you're going to give a URL here that you get from GitHub. It's right here. If you want the code, you click this code button and you say, I want to clone it by, usually it's going to be HTTPS if you want to get started with that that way. And you just say git clone, give me that, copy it. And then they'll log in with their account. So they'll say git clone that thing. Hit enter, and it'll make a new folder after you log in with your account because it's private. You got to share that repository with your partner, with your partner's account. It'll make them log in, make sure they have access, and it'll make a folder with the same name as this repository on their end at that point. So cloning for the very first time, you say git clone, and then it's a pull after that. But I use SSH. So if I wanted to get it for the first time, I would say git clone this thing. Still the same. So that's how you do that. And I think that is most of it. Most of what I would say. Are there any questions about something that I did? You'll have the video, of course, but I mean, I said a lot of words. I went kind of fast, but hopefully you see at least the use and how nice Git and GitHub could be, especially if you were working collaboratively. Even if you're working alone, it's kind of nice to be able to be like, all right, things are working right now, decently. Let me commit that change, commit the state of the world right now, so that if I mess up later, I can come back to that change and work from there again. That's another thing that's great for. All right. So yeah, definitely this is the best way to do partner work in this class. If you're working on a lab, I highly encourage you to use GitHub and Git, of course. But please make sure to use private repositories. You'll have to give access to the username of your partner, whoever owns the original repository, and then you just pull and push to the same repository, potentially using branches and merging it back into main. Yeah, just make sure to not put your code publicly on the internet because everybody's working on these labs at the same time. That wouldn't be good. Okay, so yeah, I think that's all that I wanted to say. That is GitHub and Git in a nutshell. It is very useful. Hopefully you see this picture, like it makes sense now. And you can see the point of it all. Yeah, any last questions about that? Cool, so that was fun. That was pretty much everything that I wanted to talk about today. Please do attendance if you have not yet. I'll stop that soon. And yeah, it'll just be the lectures for the day on these two wildly different topics. And we'll have another lab that I will release next time. That'll be a problem for Thursday. And just don't forget about the midterm.